All right, so let's look at the questions for section 3.2 or 3.1, sorry. So for this first question, we are given a 2x2 matrix and want to find the inverse of it. So to find the inverse of a 2x2, one of the things we need is first to find the determinant. So remember, a matrix only has an inverse if its determinant is non-zero. So the way you find a determinant is by, finding the product of these two diagonals. So 1 times 4 minus 2 times 3. That comes out to be -2. So that's not 0. So we have an inverse. The inverse of a 2x2 matrix is equal to 1 over the determinant times this matrix that's related to A. So this other matrix, what do? We take the major diagonal and swap the entries. So 4, 1, 1 here. Yeah. And the other two entries, we take the opposite. -2, -3. So this gives us this matrix, -2, +1, 3 over 2, -1/2. Now, the reason this is called the inverse is if I multiply A by A inverse, I should get the identity, that 1, 0, 0, 1 matrix there. So we can verify this through a multiplication. 1, 2, 3, 4 times -2, 1, 3 halves, -1/2. So what does this equal? Multiply row 1 by column 1, I get -2 plus 2 times 3 halves. That's -2 plus 3, that's 1. Okay, now row 1, column 2, 1 plus 2 times -1/2, that's 1 minus 1, or 0. All right, row 2, column 1, that's -6 plus 4 times 3 halves, that's -6 plus +6, 0. And finally, 3 times 1 is 3, plus 4 times -1/2, that's 3 minus 2, so 1. So confirmed that the matrix we found is the inverse of A. Right, moving on to 23. So we're essentially looking for eigenvalues and eigenvectors for this matrix. So to get that, we have to find the characteristic polynomial. So what does that look like? That is going to look like this quadratic in lambda. So the determinant of alpha minus lambda I. Let's go ahead and draw or write that matrix out. So alpha minus lambda I So what does the determinant of this matrix look like? So we're going to have 6 minus lambda times -1 minus lambda minus -12. And basically what I'm looking for, I need to look for the lambda values that are going to make the determinant equal to 0. So if I distribute -6 plus lambda minus 6 lambda plus lambda squared plus 12 equals 0. So lambda squared minus 5 lambda plus 6 equals 0. This factors into lambda minus 1, lambda plus 6, which means my eigenvalues are lambda equals 1 and -6. So part A is basically this polynomial right here. Setting that polynomial equal to 0 and finding the values of lambda, those are my eigenvalues. Now, each eigenvalue should have an eigenvector. So remember, these are the values of lambda that if I put these back into A minus lambda I, that should make this matrix linearly dependent. So first one's going to be A minus 1I. What is that matrix going to be? 5, 3, negative 4, minus 2. That doesn't look like it's going to be linearly independent. So let's see what went wrong. That doesn't factor the way that I said at all. So that should be x minus 2, x minus, or yeah, lambda minus 2, lambda minus 3. So lambda equals 2 and 3. So that didn't work at all. Let's try again. So what is A minus 2I? This better be linearly dependent. 6 minus 2 is 4, 3. Bottom row is negative 4. Negative 1 minus 2 is negative 3. All right, so these rows are essentially multiples of each other. So let's get an eigenvector here. What does this tell me? So basically, what this top row says is basically 4x plus 3y equals 0. So let's go ahead and isolate y. Actually, let's just leave it this way. 3y equals negative 4x. So that implies this eigenvector. Let's just come up with the most, like something that fits this. I believe that if y is equal to 4, then x could be equal to negative 3. I think that's a good eigenvector. So not the only one. Eigenvectors are never unique, but that is a good eigenvector. So this goes with when lambda equals 2, the corresponding eigenvector is 3, negative 4, or at least the one that I came up with. What about A minus 3I? That'll be 3, 3, and negative 4, negative 4. So again, the rows are essentially the same. One's a multiple of the other. So if I say 3x plus 3y equals 0, that yields y equals negative x, which I can write as this vector, as long as y and x are total opposites of each other. So 1, negative 1 is a good vector. And that corresponds to the eigenvalue lambda equals 3. So remember, eigenvectors are never unique, but they need to be paired with their appropriate eigenvalue. All right, that's all for 23. And now number 32. For what values of A are the vectors 2A and 4, negative 1 linearly independent? So linear independence really should happen for every single value of A except for 1. So many ways to find this out. Probably the most direct way, and the one involving a matrix, is this. Let's fill a matrix with these as vectors. 2A, 4, negative 1. A matrix is linearly independent if its determinant is non-zero. So let's find this determinant. Determinant A equals 2 times negative 1, negative 2, minus 4 times A. Let's find where this is equal to 0. So this gives me 4A equals negative 2, or A equals negative 1/2. So when A is equal to negative 1/2, this matrix is linearly dependent. So the conditions under which it's linearly independent is if A is literally anything else. If A is equal to anything else but negative 1/2, we have linear independence. All right, that is all for section 3.1.